Thank you for inviting me to ChipX. I'm not able to be in person yet, but I have been to Israel before and had a great time. I look forward to coming back sometime. I'm really happy that we are able to emerge out of the pandemic from the last year and get back to this hybrid model where in-person interaction is combined with virtual sessions as this. I'm hoping you're having a great time at ChipX so far. So today I want to give you a high-level overview of where AI is, how it came to be such an amazing and important revolution, and where we are headed next. So I like to call this the Trinity of AI. Why is it a trinity? When we think of AI, we mostly think of the algorithms, right? We think of our deep neural networks that have grown larger and larger in scale. Now we are in the era of trillion parameter models, especially language models that have become enormous. But the source of the deep learning revolution wasn't just with the deep learning algorithms and the neural networks, but also with the two other facets, data and compute infrastructure. This trinity is what helped us realize the deep learning revolution. It started with the ImageNet challenge that Dr. Fei-Fei Li created. For the first time, there was more than 1 million labeled images for training. And that's what helped us to learn features directly from data that wouldn't be possible with smaller data sets. And the third component that's often overlooked, but not for the ChipX audience, because that's very much the front and center are the chips, right? The GPUs is what created the deep learning revolution, because the parallelism that was present for linear algebraic primitives helped us train these neural network models at scale. And that also shows us having the power of unified primitives and the CUDA platform to make GPUs easily programmable was really pivotal to helping us quickly democratize AI, help us quickly create large-scale models and prototype them and move to better architectures. So that's where we see the power of hardware, the power of good AI stack, good programmable interfaces, all coming together in a very holistic manner. So where do we go from here? So it turns out with the deep learning revolution, we've seen the power of data. But what about the power of priors? This has been a mostly data-driven revolution, meaning we want to mostly not encode priors because we don't know what good priors are for domains such as natural images and language. But there can be useful priors that are structural, that are more high level rather than a detailed model. And one such prior I'll talk to you today is the use of tensors and graphs. A lot of natural structures such as molecules have graph structured data. Tensors can be realized with multidimensional data, which we'll see in a minute in more detail. And on top of it, you have other useful priors such as the laws of nature. This particular drone, apologies for the change, is governed by laws of nature such as the Newtonian laws. So you don't have to learn that from data from scratch. And in fact, for robotics, we have limited real data, and that's why we need to encode all these physics priors. And lastly, we have the ability to simulate many of the phenomena that is too expensive to collect in real life, such as data from robots and drones. So how do we enhance the power of deep learning using these simulations? So this is where we are headed next in terms of not just reliance on labeled data, but also thinking about priors that we can embed into our models, better architectural priors into our neural networks, as well as priors such as the laws of physics that can be embedded into our robotics learning. So one aspect I want to maybe dive a bit more into detail is having tensors in our learning process. So we're all aware of matrices. As I mentioned just before, the foundation of deep learning is having linear algebraic routines, which do basically matrix multiplications and other matrix operations, right? Like each layer of neural network can be realized through these matrix operations. But then why only 2 dimensions? Why not compute in more than 2 dimensions? This is mostly historic because we've limited to matrix computation in our earliest of computers. So, but now we are in the modern era. So can we scale up our chips? Can we build better hardware primitives using tensors? And how can we use that to enhance the power of AI? This is because in nature, we have ubiquitous uses of tensors, right? Like most of our data is higher dimensional. And if you think of simple data such as time series, that's just 1 dimensional. If you think of images, like especially grayscale images, that's 2 dimensional. But if you're looking at lots of rich data, such as data from autonomous driving, that's both LiDAR as well as computer vision data. You can think of other multimodal sources of information, spatiotemporal data, fMRI data. All that is highly multidimensional. So we are working on data that is highly multidimensional, but we are limiting ourselves to just matrix computation in our neural networks. How do we go beyond that to enhance our neural networks to also process in a multidimensional way? And that's where we have the power of tensors. So the basic building block for linear algebra is matrix multiplications. And I've shown this pictorially here to make it easier to understand, right? The operation involves going through either rows and columns of these matrices and doing these basic operations. But the key is to do them really fast in a parallel way on GPUs and other hardware. That's what helps us scale up these operations to these large neural networks with as much as trillions of parameters now. So how do we now take this to more dimensions? And that's where we can now do similar operations, but on tensors, right? So here we are multiplying a tensor with a vector in a similar way. But you can also now multiply tensors on several different dimensions. And so these operations are broadly called tensor contractions. And so they help us extend matrix products to more dimensions. And by building good primitives to speed up these operations and parallelize them, we can then really make these operations fast for large-scale models. And that's where, if you trace back the history of basic linear algebra subroutines or BLAS on hardware, it started with just simple vector-to-vector operations, right? And then went all the way to matrix, like multiplying 2 matrices is better hardware utilization on parallel hardware. And that's where, on GPUs, you're better off multiplying 2 matrices rather than now doing that separately as matrix vector products. But if you go now to higher dimensions, you enhance that hardware utilization. And that's where, by creating these better primitives, we can better utilize our hardware. And NVIDIA Qtensor is one such library to help really fast tensor contractions. On modern GPUs such as the A100, you can get the full parallelism and the intensity from doing these kind of tensor primitives. And most importantly, not doing any of the transpositions and doing in-place contractions. So this helps us come up with very fast tensor primitives. But how do we use this power of hardware to realize better neural networks with tensors? And it turns out that tensors can really help you compress your neural networks because you're having better priors, right? Better inductive bias in your network because it better models the multidimensional nature of your data. and also better robustness because we've incorporated these priors and better generalization. And the speed ups are a consequence of having these better hardware primitives. So that's where you have the virtuous cycle of many benefits using tensors. So Tensorly is an open source software we have created at NVIDIA. John Kosefi is the primary creator of this open source effort. I encourage you to go to GitHub and check this out. There's lots of helpful notebooks and resources available. And as you can see, we've taken a stacked approach, building from basic operations of tensors, like these products that extend matrix products, all the way to these fully prepared layers. So you can import these layers into PyTorch and run it with the rest of your neural network architectures. And so with this out of the box ability to do it and do it in Python helps you very easily get into exploring these different possible neural network architectures. As one example, we've recently taken this kinetics dataset, which is a large-scale video dataset. So video is where you can't just keep growing your models bigger, right? It's just too rich and there just aren't going to be enough parameters in your model to accurately model different video datasets. And so that's where we wanted to be able to compress, but not lose on accuracy. And you can see here, we can do as much as 30% compression and still not lose accuracy, right? So in fact, you can get much better results with the tensorized model, which even with compression, you do not lose out on accuracy. And so that's the idea. It's very simple to start with. You can start with pre-trained models. You just literally need to do one line change in your code and get this benefits of compression. So that was one great application of tensors. So what are some other applications where we can benefit from using good priors and good domain knowledge while also scaling up our operations? Another important one is robotics. I mentioned that in the beginning. We can't afford to learn from scratch in our robots because there just isn't enough data and the domain is so rich in the real world. We can have all kinds of possible changes and the long tail behavior that we need good priors. For instance, let's take this Boston Dynamics Atlas robot. It can do these impressive backflips. But on the other hand, does it have any intelligence? The answer is no, because it's completely pre-programmed, whereas the fumbling dog is intelligent because it's learning new skills, it's listening to us. So all these are qualities we'd like to see in our robots. So that's the area of embodied AI, where the mind and the body comes together. So we'd like our robots to have our instincts, to deliberate on plans like us, to understand how we behave and react, and to also be social and interact with other robots and other humans in a seamless way. And that's where NVIDIA Isac platform can really help enable this robot learning. This is an example of our partnership with BMW, where the actual factory floor now has a virtual twin that's simulated. And we have these rich, visually photorealistic simulations as well as physically valid simulations. And so by having this, you can really train your robots at scale in simulation, but then also seamlessly transfer it onto the real manufacturing floor using the EGX platform or our edge platform, using powerful devices such as Jetson or the Xavier platform, where we can enable large-scale models while also having good energy consumption. And on top of it, there's also the 5G capability with Area, where we can enable GPU acceleration also on 5G. So this aspect of connectivity, having simulations running on the edge, right? We'll see more of our operations in AI go from cloud to the edge. We'll see a lot of now devices become intelligent, what our CEO Jensen likes to call as the smart everything revolution. That'll be the next exciting revolution, where we'll have trillions of connected smart things. And that's where the edge platform will help us enable this operation at a massive scale. To show you an example of what Isac platform can do, we have this four-legged robot in simulation, and then we transfer the knowledge learned to the real robot. And what you see in this platform is having this virtual robot means we can give it a curriculum, so we can train slowly and then speed up our training in terms of different kinds of challenging tasks, right? So, and it's able to mix these different low-level primitives and be able to handle challenging situations like a frictionless surface. And whereas one that is not trained would not be able to do this. And ultimately, we can also transfer this onto the real robot. Similarly, we can also do with the robotic arm, where having contacts is a really challenging process. And if you think of like some baseline methods, it's very hard to balance this ball on top of the peg. But having like good priors, like what we call an operational space controller, and training it at scale in Isac is able to do these kind of complex tasks. And the key is also the scale. We can do this with a lot of parallelism, and with distributed reinforcement learning, we can very quickly learn these kind of complex tasks. The other facet of this is, can we also use AI to speed up simulations? So far, we said we can use simulations to train AI, but is there an equation on the other side? And it turns out, indeed, if we look at partial differential equations, for instance, that can simulate fluid flows and all kinds of complex phenomena, what we've recently shown is sophisticated AI algorithms that we've designed can predict these highly complex fluid flows. And the key is also that we are able to do this using only low resolution training data and directly be able to evaluate it at high resolution. So to complete this picture, where we are headed in future is where we'll be more on the edge, moving away from cloud to some extent, having much more smart capabilities on the edge, ultimately even training on the edge. And that's where we would need algorithms that can focus also on energy efficiency, that can do low precision training, and also realize the power of simulations. Having platforms such as Isac that can augment real data with simulations can really help us solve challenging problems such as the robot learning. And ultimately, EGX platform and other efficient hardware will help us port these models onto even tiny edge devices. Thank you so much.